Welcome, deep divers, to an exploration into the very foundation of our reality. Today we're embarking on a truly monumental journey, grappling with something that touches every aspect of the universe at its most fundamental level, quantum field theory, or QFT. Now, this framework has been incredibly successful. Absolute triumph in understanding the tiniest building blocks of everything around us and the forces that govern their astonishing dance. QFT has given us predictive power that seems almost magical, allowing us to describe phenomena with a precision that, well, it continues to astound scientists. But what if, despite all this brilliance, QFT isn't the final word on reality? What if its incredible successes are actually descriptions of the effects of something even deeper, rather than the core reality itself? That's the electrifying question at the heart of our deep dive today. We're not just reviewing QFT, we're diving into a radical new perspective that profoundly reframes and recognizes it through the lens of something called coherence physics and ontology. Our mission, as always, is to sift through the sources, extract the most impactful insights, and give you a shortcut to understanding this paradigm shift, a shift that could completely rewire how we think about the cosmos. So get ready to have your foundational understanding of reality not just shaken, but maybe fundamentally reassembled.
Indeed. And what we're discussing here, it isn't a minor tweak, not at all. It's an ontological shift, a fundamental reevaluation of what constitutes reality at its most basic level. Instead of starting with the idea of discrete particles as the primary constituents, the little billiard balls, this new framework posits that a continuous underlying coherence is the foundational reality. It's a conceptual leap for sure, but one that promises to offer fresh pathways to addressing some of QFT's most persistent and frankly stubborn challenges.
Okay, so let's unpack this. But first, let's ground ourselves in the traditional understanding, the one that has served us so incredibly well for, the better part of a century. QFT has been our undisputed champion for understanding the subatomic world. It's this astonishingly powerful theory, a brilliant intellectual feat. It successfully unifies the two pillars of 20th century physics: quantum mechanics and the peculiar rules of the very, very small and special relativity, which dictates the rules of speed, energy, space-time. Think about the sheer scale of its achievement. This framework lets us describe the behavior of fundamental particles, like electrons and photons, and the forces they exert, with breathtaking precision. It's predicted phenomena that experimentalists have then confirmed, sometimes to an astonishing number of decimal places, time and time again. This predictive power is exactly why QFT forms the bedrock of the standard model of particle physics. And that model, despite some gaps, describes almost everything we've observed, from interactions inside an atom to the properties of matter itself. It's huge.
You're absolutely right to highlight QFT's undeniable triumphs. It's a truly elegant, beautifully constructed theory. A real testament to human ingenuity, wrestling with nature's mysteries. Its ability to predict things like the magnetic moment of the electron to, 11 decimal places? Yeah. Astonishing. Or to describe the incredibly strong force binding quarks together inside protons and neutrons, a force so powerful we can never observe a quark in isolation. These aren't just technical successes. They are profound insights that have reshaped our understanding of matter and energy. However, and this is a key point, as elegant and accurate as these successes are, the question this new perspective forces us to confront is whether these very triumphs might actually be special cases of something even deeper. They are correct descriptions, yes, absolutely, but perhaps they are descriptions of manifestations, of observable effects rather than the fundamental underlying reality itself. It suggests that while QFT works brilliantly within its defined parameters, describing what we observe with unparalleled accuracy, it might be sort of overlooking a more foundational layer existence. So let me turn that back to you. What stands out to you about QFT's undeniable elegance, but also what do you think might be its subtle blind spots, especially given the persistent challenges it still faces?
That's a great question, because it really gets to the core of why this deep dive is so exciting, right?
Yeah.
For me, the sheer predictive power, especially for something like the electron's magnetic moment, it's truly breathtaking. It feels almost complete within its domain. But then, its stubborn struggle to incorporate gravity, that's a huge one. Or the constant need for renormalization, which, let's be honest, always felt a bit like a mathematical workaround, a way to fix infinities that pop up. Those have always struck me as, glaring issues. They feel less like elegant solutions and more like patches on an otherwise beautiful theory. It makes me wonder if those very patches and struggles are precisely what this new lens of coherence physics is trying to fundamentally resolve. Maybe they indicate a deeper misunderstanding of what reality is. And that, I think, perfectly sets the stage for where it gets really interesting. This is where coherence physics steps onto the scene and, as our sources describe, completely flips the script. instead of QFT being a theory primarily about fundamental discrete particles, this new lens suggests it's actually a theory of coherence fields and their discrete reductions. Now, immediately, that radical reinterpretation challenges everything we thought we knew about what's truly fundamental in the universe. It's a huge mental leap, isn't it?
Absolutely. It is a significant conceptual shift, but it's crucial. When we state, ontologically the field is coherence itself, we're making a profound declaration. The continuous underlying fabric of reality isn't composed of infinitesimal points or tiny indivisible particles or even abstract quantum probabilities. Instead, it is coherence. Imagine the entire universe at its most basic foundational level as an unbroken, continuous, dynamic state of interconnectedness and harmony. That's coherence. It's an abstract quality, yes, but it's considered the fundamental reality. It's not just a property of a field, something a field has. It is the field, the very essence of its being. Now, consider the implications for you in understanding the universe if its most basic constituent isn't stuff in the traditional material sense, but an abstract, continuous quality like coherence. It moves us away from a purely reductionist, particle-centric view where everything breaks down to smaller and smaller discrete bits. Instead, it opens up profound questions about existence, interconnectedness, even how our observation might influence what manifests. It suggests a universe where connection, not separation, is primary. So, if the field is this continuous coherence, what then are the particles we observe? Well, what we conventionally call a particle is completely reconceptualized. It's simply a coherence condensation, a discrete ripple localized from a continuous field. Think of it this way. A particle isn't a tiny, independent, billiard ball-like entity. It's more like a momentary crest in a vast, continuous ocean, or maybe a distinct ripple that appears on an otherwise smooth surface. The wave isn't separate from the water, right? It's a dynamic manifestation of the water itself. The water is the continuous medium. The wave is a localized, temporary pattern emerging within it.
That wave analogy really helps visualize it. So it's like the universe isn't made of tiny Lego bricks, but rather it's more like a giant, shimmering, perfectly tuned sound wave, maybe. And what we perceive as breaks are just moments where parts of that wave become distinct and stable enough for us to hear them or detect them.
Precisely. That's a great way to put it. To elaborate further, a particle is described as a symmetry reduction of that coherence, an eigenvalue selection. Now, what that means is that from the ocean itself remains the continuous underlying medium. The wave eventually dissipates, its energy returning to the ocean, right? In a coherence view, particles are similar, temporary condensations of the fundamental coherence that eventually dissolve back into the field. This really helps shift one's thinking from discrete objects to emergent, transient phenomena. It's a different mindset.
Wow, that's a truly powerful and elegant shift in perspective. It means that the field is coherence, and what we call a particle is merely its reduction, its localized manifestation. It's like the universe is playing a continuous symphony, and what we call particles are just the individual, measurable notes that arise from that continuous underlying melody. And crucially, it doesn't discard QFT's incredible successes. It recontextualizes them. The triumphs of traditional QFT are now seen as special cases of a deeper principle, the conservation and modulation of coherence. It's not that QFT was wrong, but perhaps was accurately describing these ripples and condensations without fully grasping the ocean they emerge from. It's a profound realignment. It suggests QFT describes the effects of coherence dynamics rather than the fundamental nature of reality itself. It transforms QFT from a fundamental theory into an incredibly accurate descriptive theory of emergent phenomena. That's a big deal. #3. Reinterpreting key QFT concepts through coherence. Okay, so with this radical new lens firmly in place, this idea of fields as fundamental coherence and particles as its reductions, let's zoom in. Let's see how it completely reshapes our understanding of the nuts and bolts of QFT itself. How do familiar concepts like interactions, quantization, mass, and even those enigmatic virtual particles look when viewed through this coherence lens? I'm particularly curious about how interactions are redefined. What actually happens when two particles interact, if they're just ripples? Does that even make sense? #3.1. Interactions as coherence exchange and resonance.
That's a vital question. And yes, it does make sense in this view. What is conventionally called an interaction is reinterpreted as the exchange of coherence fragments between fields. It's a completely different picture than billiard balls colliding or discrete particles bumping into each other. Forget that image. Instead, it's a dynamic process where portions of coherence are transferred, shared, or modulated between the underlying continuous coherence fields. And this is precisely where the role of exchange particles, the gauge bosons, gets a whole new meaning. They are now seen not as simple carriers of force in the traditional sense, but as resonant mediators of coherence flow. Think of them as the specific channels, the precise frequencies, or the harmonic conditions through which coherence is exchanged and modulated between fields. They are the conduits, the pathways for this dynamic flow. Let's make this concrete. We can use specific examples from our sources. The photon, which we know mediates the electromagnetic force.
Right. Light, electricity, magnetism.
Exactly. It's now understood as the unit of EM coherence resonance. It's the specific resonant frequency, or mode-like, a particular note in our symphony analogy, that facilitates the transfer and interaction of electromagnetic coherence. It's the very vibration that carries the electromagnetic melody, if you like. Similarly, the gluon, that's responsible for the strong nuclear force holding quarks together.
Inside protons and neutrons.
Right. The gluon becomes the unit of chromatic coherence binding. Here, color charge in QCD isn't just an abstract property, it describes specific coherence channels. The gluons are the resonant mediators, allowing coherence to be exchanged along these chromatic channels, resulting in that incredibly powerful binding force we observe within nuclei. And then we have the W and Z bosons. They mediate the weak nuclear force, responsible for things like radioactive decay. They are reinterpreted as units of broken coherent symmetry in the electroweak domain. This suggests their role is to facilitate the flow of coherence in situations where the underlying electroweak coherence has undergone a specific kind of symmetry reduction or breaking, leading to the distinct nature of the weak force compared to electromagnetism.
Wow. That's a truly profound reframing. So resonance isn't just a metaphor here. It's fundamental to how these forces actually operate. It's not just a general push or pull, but a very specific, almost tuned interaction.
Exactly. Resonance is absolutely key. It implies this isn't some haphazard exchange of influence. It suggests specific harmonic conditions must be met for coherence to be exchanged between fields, like a finely tuned instrument. For two strings on a piano to truly resonate and affect each other, they have to be at specific related frequencies, right? This isn't just a general force. It's a specific kind of tuning and harmonization between fields that allows coherence to flow in structured, predictable ways. You can imagine it like a complex musical ensemble. Different instruments in an orchestra representing the various fields are playing their own parts, but they are constantly exchanging thematic fragments or melodic ideas, these are the coherence fragments, through specific resonant frequencies. The gauge bosons are like the specific tonal qualities or rhythmic patterns that allow these exchanges to occur in a harmonized, structured way. It's a highly intricate dance of coherence where specific vibrations facilitate specific interactions rather than just a simple push or pull. It's much more subtle. Hashtag 3.2, quantization, mass, and charge as coherence properties.
Okay, that's a truly mind-bending reimagining of interactions. So what about the fundamental properties we associate with particles, the very things that define them? Things like quantization, which gives quantum mechanics its jumpy, discrete nature, and intrinsic properties like mass and charge. How are these viewed through the coherence lens? Are they also just ripples?
Essentially, yes. These fundamental properties are also reinterpreted as direct manifestations of coherence. Let's take quantization, for instance. That familiar jumpiness or discreteness we see in quantum mechanics, where energy levels or other properties only exist in specific fixed values rather than a continuous spectrum, is now explained as arising from discrete resonance conditions imposed by coherence eigenvalues. This means the universe isn't inherently lumpy with particles in the first place, but rather the continuous coherence field can only settle into certain stable resonance states, its eigenvalues, which then manifest as discrete measurable quantities. It's the stable ways coherence can maintain itself, rather than an inherent lumpiness of reality itself. Think of a tuning fork. It doesn't hum at any old frequency. It resonates at very specific stable frequencies. Those are its eigenvalues. In this view, our particles and their properties are like those stable, distinct notes emerging from the continuous potential sound of the coherence field. Then there are mass and charge. These aren't seen as inherent independent qualities of some fundamental particle that carries them around. Instead, they are defined as stable coherence reductions within the field symmetry structure, unquote. Imagine them as specific, stable configurations or states of the continuous coherence. When the continuous field undergoes a particular symmetry reduction, meaning its vast, undifferentiated coherence takes on a more specific, limited, but stable form, it can manifest a stable signature coherence that we perceive and measure as mass or charge. They are not independent properties, but rather emergent from the field's underlying symmetry and coherent structure.
Okay, hang on. So if I'm getting this right, mass and charge aren't inherent labels written on a particle, like a serial number, but rather stable patterns that the continuous coherence field adopts under certain conditions, almost like Like a specific knot tied in a continuous rope. Is that a helpful way to think about it?
Exactly. That knot analogy is quite apt. It captures the idea of a stable configuration within a continuous medium. And to delve a bit deeper, connecting eigenvalues to stability and measurability is crucial here. In traditional quantum mechanics, eigenvalues are the possible results you can get when you measure something. In the coherence framework, these are specific, stable signatures or selections that can be made from the continuous coherence field. They represent the only stable ways that coherence can be reduced and made manifest in a discrete, measurable form. These stable patterns are like the only allowed dance steps in the grand cosmic ballet of coherence. It's like a continuous spectrum of light. But when it interacts with an atom, only specific discrete colors, those eigenvalues, are absorbed or emitted because those are the stable resonance conditions of the atom's unique coherence configuration. Hashtag tag 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 3.3, virtual particles and Feynman diagrams recontextualized.
This reframing is touching everything, even the more abstract tools and concepts of QFT, like those notoriously mysterious virtual particles that seem to pop in and out of existence, violating conservation laws temporarily, and the elegant simplicity of Feynman diagrams we use to visualize interactions. They must get a fresh perspective here, too.
They certainly do, and this is a really illuminating aspect of coherence physics, I think. It demystifies some truly abstract notions. Virtual particles have always been somewhat puzzling in traditional QFT, right? Often described as popping in and out of existence for tiny moments, seemingly borrowing energy.
Yeah, it always felt a bit hand-wavy.
Well, from the coherence perspective, these are transient coherence residues, not things, but momentary asymmetry oscillations bridging field reductions. Now, crucially, they are not things in the traditional sense of being detectable, physical particles that you could ever catch or observe directly. They aren't real in that way. Instead, they are fleeting, temporary disturbances or fluctuations in the underlying coherence. Imagine the continuous coherence field briefly oscillating out of its stable state, creating a momentary ripple or blur that quickly resolves. These transient oscillations facilitate the exchange of coherence over short distances and times, acting as temporary bridges for coherence flow between more stable reductions. This reinterpretation really clarifies their often puzzling nature. It transforms them from ephemeral things into dynamic, temporary fluctuations in the fundamental coherence. They are more like echoes of potential interactions, not actual particles.
Okay, that makes so much more sense. So virtual particles are less like ghostly visitors popping in and out, and more like fleeting vibrations or ephemeral blurs in the continuous fabric of reality, just momentarily disturbed before settling back down.
Exactly. Fleeting vibrations is a great way to put it. Much better than popping in and out of existence. And then we have Feynman diagrams. These are incredibly useful visual tools in QFT depicting particle interactions. We see them everywhere. In coherence physics, they are described as coherence bookkeeping devices. Their lines and vertices are symbolic of coherence flow, resonance splits, and recombinations. They aren't tracing the paths of tiny discrete particles in the way we might initially imagine, like little balls moving along lines and bouncing off each other. Instead, you can compare Feynman diagrams to a complex map of traffic flow, maybe. But instead of cars, it's coherence itself moving, splitting, and merging. The lines represent the continuous flow of coherence, and the vertices represent points where coherence interacts, splits into different modes, or recombines. They visually represent the intricate dynamics of coherence, illustrating how it's conserved, modulated, exchanged, and reduced, rather than merely depicting particle trajectories. What stands out to you in this reimagining of these fundamental concepts, especially how it demystifies something as abstract as virtual particles?
Yeah, for me, the demystification of virtual particles is genuinely a breakthrough. It always felt a bit like a cheat in physics, These particles just appearing and disappearing when needed. But framing them as transient fluctuations in coherence, like that momentary shimmer on the continuous ocean, makes them far more intuitive, more integrated into a coherent view of reality. It transforms what felt like a mathematical fudge factor into a logical consequence of a continuous coherent universe. It's like seeing the static on an old radio being reinterpreted not as just noise, but as momentary unformatted signals that haven't quite resolved into a clear transmission yet. That feels right.
#4. QFT's major theories through the coherence lens. It's truly fascinating how this single idea of coherence recontextualizes so much of QFT, from particles to interactions, even our mathematical tools. So let's take a look at the major theories within QFT, QED, QCD, the electroweak theory, and see how they appear when filtered through this coherence lens. Do they become more unified or simply more clearly defined in their own coherence domains? And what's the real insight here for the listener, for you?
That's an excellent question, and I think the answer is probably both. They become more clearly defined as specific expressions of coherence, And in doing so, they hint at a deeper underlying unity, a common conceptual root. The key insight for you, the listener, is that these powerful theories describing different forces are now seen not as fundamentally distinct realms, but as different algebraic expressions of the same underlying coherence dynamics. It's like different dialects of the same language. Take QED, quantum electrodynamics. Traditionally, it describes how light and matter interact. Photons, electrons.
The most tested theory in physics.
Right? Exactly. Through the coherence lens, QED is reinterpreted as electromagnetic coherent algebra, U1 resonance system. What this means is that QED is essentially the precise mathematical framework, the algebra, that describes the dynamics and structure of electromagnetic coherence. The U1 group represents the simplest kind of symmetry, like rotating a perfect circle, symbolizing the single type of charge governing electromagnetism. The insight here is that the electromagnetic force isn't fundamentally about particles interacting, but about the inherent algebraic structure and dynamics of electromagnetic coherence itself, allowing for very specific resonant exchanges. Next, we have QCD, quantum chromodynamics. That describes the incredibly powerful, strong nuclear force binding quarks via gluons.
The stuff holding nuclei together.
Right. Reimagined, QCD becomes strong coherence algebra, resonance with color as coherence channels. Here, the SU3 symmetry group points to a more intricate, complex, internal structure of coherence, like twisting a multifaceted object, not just a simple circle. Color, red, green, blue, it is an actual color, of course, but represents different internal channels or modes through which this strong coherence manifests and interacts. The gluons are the specific resonant mediators allowing coherence to be exchanged along these chromatic channels, resulting in that binding force. The profound insight. The strong force, too, emerges from the complex symmetries of coherence, not merely from swapping discrete particles. And finally, the electroweak theory, which brilliantly unified the electromagnetic and weak forces, especially at high energies.
A major triumph of this standard model.
Absolutely. This is understood as a unified coherence reduction that bifurcates under asymmetry gradients. This suggests that at extremely high energies, like in the very early universe, there's a single unified electroweak coherence. But as the universe cooled, energy densities dropped, this unified coherence underwent a symmetry reduction or bifurcation. It split. This created the distinct electromagnetic and weak coherence domains we observe today. The asymmetry gradients are just the specific conditions that cause this unified coherence to split into different but still related manifestations.
That's a truly elegant way to see them unified as different branches stemming from the same initial coherence.
Maria.
Very nice. So what does this all mean for the standard model itself, which is built upon these very theories? If QED, QCD, and electroweak theory are all essentially descriptions of coherence algebras and reductions, then what is the standard model in this grander picture? Is it still fundamental?
Well, the standard model in this context is positioned as the current best fit catalog of coherence reductions into discrete forces and particles, but still incomplete. Think of it as an incredibly detailed, highly accurate inventory, a meticulously compiled textbook, maybe. It lists all the observed coherence condensations, particles, and coherence exchanges, forces, that we've managed to identify and measure so far. It's an indispensable map of the known territory. It's brilliant at that. But the crucial phrase here, and the real insight for you, is still incomplete.
Right.
If it's merely a catalog, what kind of entries might still be missing? This perspective immediately opens the door to deeper physics beyond the standard model. It suggests that while the standard model is phenomenal at describing the manifest effects of coherence reductions, it might not fully describe the entire invariant coherence field itself, or all the possible ways coherence can manifest. It strongly hints that there are likely other forms or reductions of coherence out there.
Which could explain things like dark matter, dark energy.
Precisely. Things the standard model currently cannot account for. It provides a powerful conceptual roadmap for where future physics might need to look beyond just cataloging the ripples we see now.
Okay, it's clear that coherence physics provides a powerful framework for reinterpreting QFT's successes. That's fascinating. But QFT, for all its unparalleled achievement, isn't perfect. We touched on this. It has some notorious persistent challenges, open problems that have plagued physicists for decades. Things like the infamous problem of infinities, its stubborn struggle with gravity, and the ultimate quest for a unified theory. How does coherence physics, with its radically different ontology, offer entirely new perspectives and potentially entirely new pathways on these long-standing roadblocks? Let's start with the infinities, that infamous problem. In traditional QFT calculations, when you try to calculate interactions, especially at very small scales, you often end up with mathematical expressions that just blow up, that yield infinite results. These clearly don't make sense in the real world. Physicists developed this clever but somewhat unsettling technique called renormalization to tame these infinities, basically subtracting them away to get finite measurable answers. But it always felt a bit like, well, like sweeping fundamental divergences under the rug. How does coherence physics view this profound issue? Does it just disappear?
Well, it doesn't just disappear, but it's viewed very differently. And this is one of the most compelling aspects of the coherence view, I think. From this perspective, infinities are residues of treating coherence reductions as absolutes rather than relational. Let me unpack that. The problem isn't that nature itself is infinite in some paradoxical way. The problem, as interpreted by coherence physics, lies in our method of describing it, in the assumptions baked into our models. When we treat particles and their properties as absolute independent entities, as absolute reductions of coherence, divorced from their continuous origin, we implicitly introduce these mathematical divergences into our equations. The source material states, properly, coherence dynamics are finite, but reduction methods impose divergences.
Ah, okay. So the math breaks because the concept is wrong.
Kind of, yes. It implies that the fundamental continuous coherence dynamics of the universe are inherently finite and well-behaved. No infinities there. The infinities only appear when our mathematical models try to force discrete absolute boundaries onto something that is fundamentally continuous and relational. It's like trying to measure the coastline with a tiny rigid ruler. The smaller the ruler, the longer the coastline seems, approaching infinity. The issue isn't the coastline, it's the measuring method. This suggests a fundamental misunderstanding in our approach. We view reductions as distinct, absolute things rather than dynamic, interconnected parts of a larger, finite whole. This offers a profound insight. The issue isn't with reality, but with our current conceptual framework for describing it. The solution isn't just to subtract infinities, but maybe to change the underlying ontology, the starting point.
Okay, that's a fresh take on renormalization. Now, what about the other gargantuan hurdle for QFT? Its stubborn struggle to incorporate gravity. Unlike the other three fundamental forces, electromagnetic, strong, weak gravity has stubbornly resisted all attempts to be described by a quantum field theory. No accepted quantum theory of gravity, no confirmed graviton particle. For decades, this has been arguably physics' biggest puzzle. How does this new coherence perspective explain that profound failure? Why doesn't gravity fit the QFT mold?
This is where coherence physics offers a truly profound departure from traditional particle physics, and it directly explains QFT's failure with gravity. It states that QFT cannot incorporate gravity precisely because gravity is not a particle force but a coherence structuring principle, hypergravity invariance.
Whoa, okay, unpack that. Not a particle force, a coherent structuring principle.
Exactly. This is a radical reimagining. If gravity isn't mediated by a particle, like the other forces are with photons or gluons, then QFT's entire particle-centric approach, its whole methodology, is fundamentally incompatible with it. It's trying to fit a square peg in a round hole. It's like trying to describe the architecture and stability of a grand cathedral using only the concept of individual bricks, completely missing the blueprints, the overarching structural principles, the engineering that organizes them into that shape. What might hypergravity invariance entail? Well, it suggests a global, structural, and unchanging role for coherence throughout spacetime itself, rather than a localized exchange of a particle. Imagine gravity not as individual threads pulling things together, but as the fundamental, unchanging weave pattern of the entire cosmic fabric. It's an invariant principle that dictates the very architecture and dynamics of spacetime, how it curves, how things move within it, rather than just the local push-or-pull interaction between discrete particles. This perspective fundamentally shifts our understanding of gravity from a localized interaction to a pervasive structural attribute of cosmic coherence. A fundamental aspect of reality's very organization, not just another force within it.
Okay, if gravity isn't even a force in the same sense, that changes everything for unification. The ultimate holy grail of physics, right? The quest for unified theory of everything, a single elegant framework describing all forces and particles. What does coherence physics suggest such a theory must achieve to truly be considered complete and, well, everything? What does unification look like now?
From the coherence perspective, the true theory of everything, or TOE, must unify coherence conservation across all reductions, standard model and relativity as partial appearances. That's the grand, ambitious vision. It means that the standard model, which so accurately describes the forces and particles of the quantum realm, and general relativity, which describes gravity and the large-scale structure of spacetime, are not the full story. They are described as partial appearances. Incomplete, albeit highly accurate, descriptions of a more fundamental underlying coherence. They're like shadows on the cave wall. This framework provides a conceptual roadmap for how such a grand unification might occur. It's not about finding a single particle that mediates all forces or one single equation that magically contains all others. Instead, it's about identifying the overarching principle of coherence conservation, how coherence is preserved and expressed across all its manifestations, all its different reductions. This includes bridging the discrete phenomena of the standard model with the continuous structural effects of gravity described by relativity. It suggests a search for a meta-principle, a universal coherence that gives rise to all the phenomena we observe, unifying the quantum and gravitational realms as different expressions, different facets of the same fundamental reality. It's a vision that seeks the underlying blueprint for all of existence, the source code, if you will.
This has truly been an incredible journey, fundamentally shifting our understanding of the universe at its most basic level. It's a lot to process. Let's try to bring this full circle now. What is the overarching conclusion about QFT's place in our understanding of the universe when viewed through this radical new lens of coherence physics? Where does it fit in the grand scheme? Is it still important?
Oh, absolutely still important. But the main point, and it is a profound one, is that while QFT is extremely precise within its scope, it is not the deepest layer, but a derived description. This doesn't diminish QFT's incredible achievements, not at all, but it fundamentally repositions them. It suggests that QFT is describing the observable, measurable effects of a more fundamental reality. Much like a shadow accurately describes the presence and movement of an object without being the object itself. It's a masterful description of the shadow, but not the deeper reality casting it. Let's just quickly summarize what QFT does achieve within this new framework, because its descriptive power remains unparalleled and indispensable. We shouldn't forget that. First, it models coherence condensations as particles. QFT accurately describes the discrete ripples, the localized manifestations of coherence that we perceive as particles. It gets those right. Second, it encodes resonance flows as force carriers. QFT correctly identifies and quantifies the specific resonant mediators, the precise frequencies and channels that facilitate the exchange of coherence fragments, which we call force carriers. It gets the interactions right in that sense.
Got it.
And third, it quantifies coherence eigenvalues as measurable constants. It pinpoints and measures the stable, discrete resonance conditions emerging from the continuous field, which we know as the fundamental constants and properties of particles. It gets the properties right. However, and this is crucial, QFT omits two critical elements that are central to coherence physics. It omits the invariant coherence field, zeta naught, and the observer-driven symmetry reductions that give rise to all measurable effects.
Okay, zeta naught and observer-driven symmetry reductions, those sound like potentially huge emissions. Can you elaborate on what exactly they mean for us, for the listener? What are we missing in standard QFT?
Absolutely. Let's take zeta naught first. This is the proposed underlying invariant coherence field, the continuous, unbroken, primordial ocean of coherence that QFT in its traditional form doesn't explicitly account for. QFT describes what happens within this ocean, the waves and ripples, but not the ocean itself, its intrinsic nature or its undifferentiated state before any manifestations. Imagine it as the absolutely calm, undifferentiated potential of the universe before anything began to ripple or condense. The potential before the actual. It's the background hum, the primordial state of coherence from which everything else emerges. And QFT simply starts describing the music once it's already being played without acknowledging the silent stage it's on or the potential for silence. And then there's observer-driven symmetry reductions. This is perhaps the most radical and thought-provoking omission. It suggests that the very act of observation, or perhaps the existence of conscious systems, isn't just passively recording reality, but plays an active role in selecting specific, discrete manifestations from the continuous coherence field.
So, consciousness collapsing the wave function, but on a deeper level.
It's related to that idea, but perhaps more fundamental. It's not necessarily about the observer creating reality out of nothing, but rather about the act of perceiving or interacting, helping to solidify or reduce the infinite possibilities of coherence into the discrete realities we measure and experience. Think of it like looking at one of those fuzzy optical illusion images. Your brain actively collapses the myriad possibilities of what it could be into one clear interpretation, right? It resolves the ambiguity. What if our universe, at its most fundamental level, operates on a similar principle, where the act of perceiving helps solidify those potential ripples into what we call particles and forces? It implies that what we see as solid particles or distinct forces are, in some sense, selections or reductions made from an infinitely richer, continuous underlying reality, potentially influenced by the observer or the interaction itself. It's a mind bender. Therefore, the conclusion is clear. QFT is fundamentally, ontologically downstream of unified coherence theory. It means QFT is an incredibly powerful tool for describing the effects of coherence reductions and their dynamics, but it doesn't describe the fundamental cause or the underlying invariant coherence that gives rise to everything. It's a masterful description of the shadow, yes, but not the deeper reality casting it.
That's a truly profound thought, and it leaves you, our listener, with an incredibly powerful question to ponder. What if everything we call a particle, every force we feel pulling or pushing, every interaction we measure, is merely a ripple, a local condensation, a temporary crest in an infinitely vast and continuous engine of coherence? And what if our very act of observing, our attempt to measure and define, is part of what makes those ripples appear as distinct entities from that boundless ocean? It leaves us with a profound question of the true nature of reality and our own elusive, perhaps even participatory, role within it. Definitely something to think about. And that brings us to the end of this mind-expanding deep dive into coherence physics and its stunning implications for quantum field theory. We really hope this exploration has given you a fresh, maybe even radical perspective on what might truly be the deeper layer of reality. Thank you for joining us on this journey, and we encourage you to continue pondering this radical reimagining of the universe's fundamental principles. Until next time, keep exploring the deep.